So, hello everyone. My name is Jinzi, and the co-author Hugo van Ham is my supervisor. Both of us are from Leuven of Belgium. The topic of the presentation would be speech disorder classification using extended factorized hierarchical variational autoencoders. And this is outline. Okay. Speech disorder could be caused by many reasons and include many types. For example, like the dysphagia and laryngectomy and cleft and hearing impairment. With development of speech processing technology, it's possible to achieve automatic speech disorder type classification using neural networks. Common neural networks like convolutional neural network, bidirectional LSTM, or the residual network all require a large amount of labeled data. But for speaker with speech disorder, we all know it's difficult to get sufficient data and reliable label. So autoencoder as a self-supervised model could be a better choice. And in this research, we mainly study an evolution of the autoencoder, which can disentangle the speaker characteristics and content, which is the Factorized Hierarchical Variational Autoencoder, and FHVAE for short. Here is the data flow of a basic FHVAE model. The input of the model is 200 million, in our case is 200 million seconds of audio. Here we call it one segment. Then the FHVAE model encodes it into two latent variables. The sequence-related latent variable Z2 should contain the information of the whole sequence, for example, the recording environment or the speaker's characteristics. And the segment-related variable Z1 is conditioned on Z2 and is supposed to contain information only in this segment of the whole sequence. Then the decoder could reconstruct the input feature based on these two latent variables. The loss function of the model would consist of two parts: the variational autoencoder lower bound, which guarantees the whole model perform as a variational autoencoder, and a discriminative loss of the Z2 variable, which encourages the separation in the Z2 space, which means we should be able to infer the sequence index or speaker ID from the variable Z2. So the FHVAE model hence tried to disentangle the speaker characteristic and content from the speech representation. If the disentanglement is perfect, the Z1 variable, which is only segment related, should be speaker independent, and we should know what is said in this segment, and we could do ASR, and only Z2 would contain the speaker characteristics, and for disastric speech, we could do diagnosis or assessment of severeness or things like intelligibility score, things like that. However, the speaker with a speech disorder exhibits a vowel triangle smaller than the normal speaker, like this figure, which means the speech disorder should be reflected also in the segment-related variable Z1. So the goal of the whole research is to force all speakers to use the same content space, which is the Z1 space, which means that the speech disordered version of a phone should be in the same place in the Z1 space as the normal version of a phone. And only variable Z2 would contain the disorder-related information. To achieve this, we take a first attempt in this work. We add the regularizations to the two latent variables. we force the variable Z1 contain the phone label information, and force variable Z2 contain the speaker ID. The two regularizers are actually two single-layer classifiers, and the cross entropy between the predicted and ground truth label distribution is added to the loss function as the so-called regularization loss of Z1 and Z2. Then we would like to evaluate how the extended model could disentangle the input speech. We first train the FHVAE model with a dataset called Torgo. Torgo dataset consists of English speech data from speaker with or without dysuria, and because we need phone label for regularization, here we only use the part that contains the phone level alignment info, and it's about 4 hours long. And the regularization terms we use in Z1 is 49 phones, and in Z2 it's 11 speaker IDs. Then we use the well-trained FHVAE model to extract the Z1 and Z2 variable from a new dataset, which is Corpus. Then we use the extracted variable to train a speech disorder type classifier. Then we hope, by checking the classification accuracy, we hope we could know how much disorder-related information exists in each latent variable, and therefore we could infer the disentanglement performance of the FHVAE model. The Corpus dataset is a Dutch speech dataset of speaker with or without speech disorder. It contains 7 categories of speech disorders, but to guarantee the minimal size of the dataset and to form a balanced dataset regards the disorder type, we only use the 4 types of disorder speaker and the normal speaker, and we choose randomly 29 speaker from each type. Then in total it's 1.6 hour long, which could be insufficient to train a classifier. So we augmented the data by changing the speech rate. So the augmented data would be 8 hours long. Then let's see the classifier. The classifier is 2 dense classification networks, one with 100 units and ReLU activation, another is the output layer with softmax. The experiment is in 6-fold cross-validation form, balanced in disorder type, and we calculate the mean accuracy over the 6-fold as a metric. We use a single Z1 and Z2 variable as a classifier input, and we also consider to use the concatenated variable Z1 too, which contain information from both Z1 and Z2. But notice that these 3 variables are all from 200 millisecond speech, which could be difficult to accurately classify the disorder type. So we also aggregated the variables over word or utterances level by unweighted mean or attention-based mean, and we also tried the standard deviation for the Z1. Here, let's see some results. The first part is about how effectiveness the Z1 regularization in rearranging the disorder-related information in the latent space. In this figure, the x-axis is the Z1 regularization loss weight in the FHVAE model training, and the y-axis is the classification accuracy used the latent variable extracted by the FHVAE model trained corresponding to the to the corresponding loss weight. Here we see with low Z1 regularization, the two high accuracy points is actually from Z1, which actually should be the segment-related variable, and the two low accuracy point is from Z2, which was supposed to contain the speaker characteristics. So actually, when we have low Z1 regularization, the FHVAE model actually falls in building a speaker invariant Z1 space. Then by increase the weights of the Z1 regularization loss, we could see that the accuracy using Z1 decreases and the classification accuracy using Z2 increases, which means with high Z1 regularization, which means that the high-weighted Z1 regularization succeeds in moving disorder-related information from Z1 into Z2 and build a more disorder invariant content variable. And this figure has the same x-axis with the last one, which is also the Z1 regularization loss weight. And the y-axis here is the Z1 regularization loss value in the toggle validation set. Because as we mentioned, the regularization loss is actually the cross entropy between the predicted and the ground truth level of the phone in this segment. So when we have a higher Z1 regularization loss weight, we see the cross entropy between the predicted and the ground truth actually have a decreasing trend, which means that the Z1 now performs better in phone classification. So we choose the highest loss weight 1000 in this case, and for further classification, here we provide the classification accuracy using MFCC and Z1 and Z2 extracted from the basic FHVAE model as a baseline, and also the Z1 and Z2 from the extended model. Let's first see that the Z1-2, which gathers the information from both Z1 and Z2, performs better than single Z1 or Z2 as expected. And also the input that's aggregated within one word or one sentence also performs, in most cases, also performs better than the single segment. Then let's only focus on the sentence level thing to make things easier. Here we see that the latent variables extracted by FHVAE model shows an advantage in classification accuracy over MFCC features. And the Z2 variable of extended model gives better accuracy than Z1 and the basic model variables. Then let's see the conclusions. First, in this research, we apply the FHVAE model to disordered speech data, and we hope it could disentangle speech characteristics and the content information. And we see FHVAE model with regularizations does succeed in disentangling the who, the speaker characteristics in Z1, and the what, the content information in Z2. Sorry, I made a mistake. In disentangling the who in Z2 and the what in Z1 better. And the Z2 extracted by the extended FHVAE model shows better disorder type classification. But I like to mention that in this experiment, we also use the label data, so it's not a self-supervised model. And I need to point out that we only get like 0.67 as our highest accuracy, I know it's not a perfect accuracy, but we do have a fair agreement between the predicted and ground truth disorder type label. Consider the chance level of 0.2, and this could be I would say it's a successful step towards our final goal, which is ASR in the content variable Z1. Thank you.
Thank you very much. So we have a remote question from Nina Benway.
Yeah.
Thank you for this talk. What is the metric reported for classification accuracy on slide 15?
Slide 15. Yeah. So accuracy is we count the number that the classification classified accurately, correctly, and divided by the whole sample we use in the test set. Then, because it's 6 folds, we use 4 for training, 1 for validation, and 1 for test. So we calculate the average over the 6-fold to produce this classification accuracy metric. Yeah. So it's simply just accuracy.
Very nice talk.
Thank you.
You didn't mention, I guess, the types of speech disorders.
Yeah.
I guess this is fine. If you're looking at, I guess, the variational autoencoders, I guess one task is to do kind of the screening process to basically say it's healthy or neutral or potentially disorder. So that type of task is very different than classifying the individual types of disorders, which is what I think you're trying to do.
We actually trying to classify the 5 types. It's not like normal or disordered. It's 5 types.
So normally, I mean, there's a wide range of speech disorders,
yeah.
And they're not consistent, obviously, between speakers and also with age and other factors there. So I think there was an earlier question on when building a single system to try and do a lot maybe doesn't always give the best performance. So maybe comment on how your approach can generalize over that range of disorders. Or if the screening is a better option.
Okay, yeah. Okay, thank you. We would definitely consider that. Yeah.
Yeah, thank you for your interesting talk. I have a question related to the second graph that you presented in the table. My question is, it is an open question. Is it possible to provide confidence intervals to these numbers in order to be really sure about what is improvement and what is not an improvement? Is there any MC-like procedure possible to computationally provide intervals, do you think?
So do you mean the accuracy things or the...
Yeah, for example, take your second graph, which was, I forgot actually. Yeah, this one, yeah. For example. So if you have confidence measures, yeah. Intervals, you are sure about whether there is a declining effect or whether this is coincidental. And so if any procedure can provide us with some vertical interval, then you are in a better position to assess this tendency. And my question was, is it possible to have a sort of Monte Carlo like?
Yeah, I think I get your point. Actually, the reason we tried to plot this figure is that we worried that the high Z1 regularization will somehow destroy the information, content information in Z1. So I think if the thing didn't goes up, it's not by the result. And in this case, although it goes up sometimes, but I think the trend is normally decreasing. And I think consider our training data, amount of training data, I won't. It's possible, but I think it's not like a coincidence. Yeah. Thank you.
That's okay. I was just wondering, for the Z1, Z2 representation, you don't need any of the disorder information to train that system, actually, right?
We did use the speaker ID, but in our work after this, we found the speaker ID is actually not really play a role. Yeah. Okay.
Let's thank
Thank you.
speaker.
Thank you.